Hello and welcome to this video. In this video we are going to go through the process of nuclear fission. Now we've mentioned fission very briefly in a previous video, and we've said that nuclear fission is basically when we split a nucleus. And so what we're going to say now is, how exactly is that possible? How do we split a nucleus, and more importantly, how do we get energy out of that? How do we receive energy when a nucleus splits? And how we are going to do it first, our process is we have to take a very large nucleus, usually, so we start with a very large nucleus, and usually we will use a certain isotope of uranium, which is uranium 235 with 92 protons. And this, as a nucleus, is fairly large and also fairly radioactive. Now, we don't want it to just emit radiation. We want it to exactly split into two separate nuclei. So how we're going to do that is we first need to make it even more unstable than it already is. Now, this is a very, very big molecule, so it's on the verge of breaking the barriers of the strong nuclear force anyway. So what we need to do is add in an extra neutron. So this is a single neutron, and this is a slow-moving neutron. Now, these neutrons have to be slow so that they can be absorbed. If we have a neutron that's moving too quickly towards this nucleus, it's just going to undergo a collision and bounce straight off the other end. It can't be a proton, because then we're going to have to fire it very quickly at this nucleus in order to overcome the electrostatic repulsion. So we just have a slow-moving neutron that slowly gets closer and closer to the nucleus until it's within a range that it becomes absorbed into the nucleus. So it gets absorbed. So it's absorbed by the uranium-235, and this then turns into uranium-236, 92. And uranium-236 is unstable. This is no longer stable as a molecule, or as an atom, or as a nucleus at all. Okay, so this is where we've introduced that just a slightly higher level of instability that is then going to cause this whole thing to split into two daughter nuclei. Now, what it splits into is again down to chance, but by probability we can see that one possible way that this can happen is it can split into barium with 144 nucleons and 56 protons. So this is one of our what we call daughter nuclei, and our other is krypton 9036. So we have two daughter nuclei. Now, what you'll notice about this is if I add together their proton numbers, I get back to 92. However, if I add up their mass numbers, I get to 234, not 236. Now, what I'm saying here isn't that I've completely obliterated two neutrons in this. That's just not possible. We're not on that kind of energy scale, and we don't have any antimatter present. So what that means is I also have to have released two more neutrons. So I have two neutrons released in this initial fission reaction, as well as some energy. This is where our energy will be released, and we'll quantify this energy in just a second. Now, when this happens, these two neutrons will then continue on, and maybe we'll have another uranium-235 that will be absorbing one of these neutrons. So these will continue and are absorbed by other uranium nuclei, and this leads to a chain reaction. Okay, now this chain reaction is a good thing and a bad thing. The good thing about this chain reaction is that we don't have to keep adding in more neutrons. We don't have to have an endless supply of neutrons to make this work. If we put in one neutron, we're going to get two neutrons out, which means we really only need one neutron for this whole thing to occur. Granted, if we only have one neutron in this, it's going to be very slow, but it will speed up over time. The bad part about this chain reaction is thinking about what is coming out at each interval or each time a fission reaction occurs. If we make the assumption that it will be a regular time interval, we start with one fission reaction, we get one spike of energy. Then the next time a fission reaction happens, two of them happen at the same time. Those two are going to release double the amount of energy that we released at the start. When those two undergo, they will each produce two more. We now have 4 fission reactions going on at the same time, 4 times the amount that we get. This is then going to be exponential. If we then have 10 times the amount, we get 2 to the power of 10. So just by going 10 forward, we've now got a much, much bigger amount of energy. And if this continues, if we think we're on the scale of Avogadro's constant amount of molecules, so we have roughly about 6 times 10 to the 23 molecules in here, this then means we're going to get to very, very, very high levels of energy very, very quickly. And this is nuclear energy, and that is how you form an atomic bomb. So the chain reaction needs to be controlled. And we will look more about how that needs to be controlled when we look at the thermal nuclear reactor. And so I will save that for that video. So I will refer you to the thermal nuclear reactor to see how we actually control that. But for this video, we now have an idea of what fission actually is. It is simply just the idea that we take a large unstable nucleus, we push it a little bit further by having it absorb a slow-moving neutron. It then becomes even more unstable, then splits into daughter nuclei and releases some excess neutrons, which will then continue on in a chain reaction, as well as producing some energy. Now we need to see, how do we actually calculate how much energy is being produced, or why should energy be lost in the first place? Now this, I'm going to refer back to this idea of binding energy. For binding energy, we said that the amount of energy that it requires to hold the nucleus together is going to be different for every nucleus that I have. What I find is that if I split this from uranium 92 to 35 into it was barium 144 56 and krypton 90 36. If I were to find the total masses of these two guys, so the total mass here, the mass, and the 3 neutrons as well, or 2 neutrons even, which will have 0 protons and 1 of these. If I were to find the total mass of this, which I'm going to call, actually let me be specific, it's the mass of barium plus the mass of krypton plus the 2 times the mass of a neutron, and I were to find the mass of uranium, which I'm going to call mass U, I would have some difference between these. These masses are not equal to each other, and this is what's known as a mass defect. Now that mass defect occurs due to actually the excess energy that is inside a nucleus, due to things like the gluons or the pions that are going to keep these things together, keep the nuclei together. Now, by having less gluons present, I have less energy present, and as we know from the previous video, this is mc squared, so if I have less energy, I have less mass. Now what this means, I have less energy in barium and krypton and a neutron individually than I do in a single atom of uranium or a single nucleus of uranium. So I can calculate the mass defect, which is just basically the change in mass of these things. Now, usually the change in mass will be given in terms of the atomic mass unit. Now, what I'm going to say is that I know it's the difference between these two. I am personally I already know that the mass of barium plus the mass of krypton plus the mass, or 2 times the mass of the neutron, is going to be larger than the mass of uranium. So I'm going to do it this way around. If you can't figure out which one is bigger than the other, first calculate them both and just take the difference from the bigger one to the smaller one. In every case, you will most likely end up with this idea that the products will have a bigger mass than the whatever you start with. But even if you get a negative answer, this mass defect always has to be positive. So no matter what, even if you put these the wrong way around, you always just take the positive answer. And the reason this has to be positive is because we're going to say it's directly proportional to energy. And if that is the case, that means that we would be saying we have negative mass energy, which is not a thing. That's not real. Okay, so even if you put these into the calculator the wrong way around, or you say maybe the uranium has a bigger mass than these 3 combined, you would then have to basically just take the positive, get rid of the negative sign. And then that means that the amount of energy that we release is based on the change in mass of these 2 things. So I can then say the energy released is just going to be the mass defect multiplied by c squared. Okay? Now, usually what I find for fission is that I will generally get a energy of around 0.5 mega electron volts. Now, this is not is a pretty large amount of energy, but you'll find when you look at the fusion video that this is not as much energy as fusion, and we will look there as to why we don't have fusion every day rather than fission. But this is a very large amount of energy, and the kind of benefit of this whole fission process is we don't exactly need a lot of fuel. We don't have to burn loads of crude oil or anything. We can have a handful of atoms, maybe a kilogram of atoms. We've then got more than enough atoms to create a massive amount of energy. And so by doing that, if we can keep it in the right conditions and have the right efficiency, we can produce very high amounts of energy. The problem is, this is nuclear energy. There tends to be a whole kind of stigma in the public eye of all of the dangers of energy. But as we've seen in the dangers of radioactivity video, those can be reduced or even neglected in some cases based on things like having thick lead walls or having thick sheets of concrete. And again, I will refer this all the safety features of this to the thermal nuclear reactor video. And with that, we can now explain the process of fission, and we can calculate the energy that is released, and this is a common question that will come up on this kind of thing. Thank you for watching.